Okay, y'all, we're going to start looking at actual Newton's first law, but because we don't trust some dumb old textbook, we're going to actually look at Newton's first law. We're going to trust some dumb old Latin translator. Every body preserves in its state of rest or of uniform motion in a right line, perseveres in its state of rest or of uniform motion in a right line, unless it is compelled to change that state by forces impressed thereon. So, end of video. Just kidding. There's cuckoo clock again. End of video. Okay. So let's talk about what that means. So I think what your book says, now we're going to go look at your book. Okay, a body at rest tends to stay at rest. Now people get really up in arms about making sure you know which law is which, and like somebody's going to be, well, like that violates the first law of motion, and you're like, well, which law of motion is that again? Then they're going to be like, you don't know what you're talking about, and you're like, dude, it doesn't matter. I know how to apply them. I don't need to know what they're called. But you're going to look stupid if you don't know this. So the first thing you have to basically, so think about it in this order. First thing you have to know is that if something is not moving, then it doesn't move. Or if something is in motion at a constant velocity, unless it's acted upon by an external force. So it's that whole thing of like, you know, if you were on an icy pond and you put a ball and you push the ball and it was actually frictionless, the ball would go forever. Or if, you know, you're in space in between enough planets and stars and stuff, you could just push a ball in space and it would go whoo like that forever. Which I think is what Voyager? Whatever that, I think it was Voyager, that space thing is spacing, because we just pushed it and now it's going out forever until something has an effect on it. And if we made it stop, it would actually just stop. There are actually places in the universe or in the solar system called Lagrangian points, where like the net force on those points is zero, so they don't move. They just don't move. It's so weird. There's like nothing there. They are just spots that if you put something there, it would be there like 10 millennia from now. I don't know what a millennia is. Okay, so since we're looking at these, first law of motion, you have to know if something's not moving, it stays not moving. If it is moving, it stays moving exactly the same. But the constant velocity part is super important. And if you don't know the constant velocity part, that basically means in order for something to move, the sum of the forces have to have non-zero to accelerate. So if the forces are zero, acceleration is zero. But we're actually not this. This is the next law of motion. Okay, so first of all, we've observed the universe that if we're not touching something, it's not moving. Okay. And when I say not moving in physics, that also means moving at a constant velocity sometimes, when we're talking about forces at least. Okay, now Newton's second law, somewhere, let's look what it says over here. Newton's second law is the alteration of something, something, something. Come here, girl. Oh my goodness. There it is. Okay, law 2. The alteration of motion is ever proportional to the motive force impressed and made in the direction of the right line in which force is impressed. Okay, that means that, okay, so again, we've assumed or we've established that something will not move unless we put a force on it, right? Okay, so Newton's second law says, well, the only way that you can get something to move is if you have non-zero forces, okay? And he said that it's proportional, but he didn't explicitly, I don't think, say what it was proportional to, but the motive force is impressioned. Okay. But eventually, and I don't know if he figured this out or somebody else or whatever, if it's not zero, then whatever those forces are is equal to the mass times the acceleration of the object. Okay? And this is where it can get a little bit weird, because if we're looking at sum of the forces equals mass times acceleration, so if the sum of the forces on an object is non-zero, then it is accelerating in that direction. And so you'll usually see it written like this. And then we'll be like, okay, what are the sum of the forces in the x direction? Blah, 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 blah. So if it's accelerating in the x direction, it'll have an acceleration in the x. If it's accelerating in the y direction, it'll have that. Now, a lot of times in that other chapter, we said acceleration to y is negative 9.81, but that isn't always the case. Okay? So, but like if I'm sitting on the ground, then the sum of the forces in the y direction are, if we draw our little free body diagram, is weight and normal. So it's minus weight plus normal. And since my acceleration is 0, it's mass times acceleration in the y, but the acceleration in the y is 0. Does that make sense? So that's how I know that my normal equals my weight force. Okay, but if I had that same box, come here, girl. If I had that same box and I'm looking at it in the x direction, maybe there's a force pulling on it, and the force is, you know, I don't care, 30 newtons, and it has 20 newtons of friction on it. Then I could be like, well, how fast is it going? Because obviously I'm pulling on it more than the friction is working against me. So notice how I don't even have the weight and the normal on here because, I mean, it's bad form, but technically it doesn't matter because I'm only looking at the forces in the x direction. So there's 30 going forward, there's 20 going back, and let's just pretend that this is 10 kilos. So that's going to be equal to 10 kilos times some unknown acceleration in the x direction. Okay, notice I use 10 kilos because that's the mass, not force. So if I had instead said that it was 10 pounds and everything was in pounds, then I have to be like 10 divided by 32.2 to get the slugs. So if I had said 10 pounds, I would have needed to insert 10 over 32.2 to convert pounds to slugs because I need it to be a mass. Okay, so then I have 10 equals 10ax. I didn't actually do that on purpose. So 10 equals 1 meter per second squared. So as long as those same forces are applied, this thing is accelerating at 1 meter per second squared. Kind of? Sort of? Okay, so that's Newton's second law. So the first law was things don't move things don't move if there's no forces on them, or if the forces add up to 0. His second law is, well, if they don't add to 0, then it's basically mass times acceleration. I don't know if Newton said the mass times acceleration part. He really just wimped out and said that it was proportional, but we're going to give him credit. So that's Newton's second law. And then Newton's third law is somewhere. Somewhere? Is there a third law? Oh, we're still in the second law. Man, there's a lot of Newton's second law. Derp, 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 mass and weight. Come on, girl. So here's Newton's third law. I was actually going to get into this, but now that I'm looking at it, I'm going to not get into this until we actually get to it, because it actually doesn't have anything to do with motion. It just has to do with forces. So Newton's first law, if stuff isn't moving, it has no acceleration. Or if it's moving, but it's, again, you have to remember that for the purposes of forces, if something is not accelerating, it's still, right? Because, like, technically, we're all sitting on this earth, and we are accelerating, but from our reference frame, we're not accelerating because we're like, but we're all just sitting here. Nothing exciting is happening. We don't see that acceleration. Some of the forces in our reference frame is 0. So our acceleration in this reference frame is 0. That's the first one. If the sum of the forces is 0, it's either not moving or is a constant velocity. The second one is if the sum of the forces is non-zero, then that equals mass times acceleration. Acceleration. And the big deal on that is to make sure whenever you eventually start doing math with this that you use the actual mass and stuff. And then the other big part, and I've kind of glanced over it, is that it all works in different directions. So these are really vectors. So whenever I say the force of the, or the sum of the forces in the x, that could be 0, while the sum of the forces in the y direction might be non-zero, in which case it'd be equal to mass times acceleration, but that would only be acceleration in the y direction. And then, you know, if I had the z direction, I can look at the sum of the forces in the z direction, and maybe that's 0 as well. So it basically means that we can evaluate each of the directions, again, assuming that the directions that we're looking at are all perpendicular to each other, and we can treat them all separately. So hopefully that's just a basic, but if anyone ever asks you the first one is they all at the 0 if they're not moving or constant velocity. The second one is, well, if they're not 0, they're accelerating. If they're not moving or constant velocity, then they're accelerating. You're like, thank you, Newton, for coming up with that. And then the only way that that can happen is if the net force on the object in that direction is non-zero.